Welcome to our follow-up presentation from last AstraCon. We're going to be talking about Asterisk on Kubernetes, primarily around infrastructure and automation. And we're going to have 4 sessions today. So the first one is going to be the technology overview. So this can be mostly presentation material here at the beginning. And then after this, we'll go into talking about Ansible Playbook Bundles, and which will have a component of presentation material, and then we'll do a demo. There will be a lunch. Then we'll talk about operators, which will have a presentation and a demo component. And then in the final session, it's just going to be open-ended, kind of hack session. We'll show you everything that we've done. We can spend more time deep diving into the components that we aren't going to have time to go into when we're doing the presentations. And it's just going to be free form. If people want to follow along and build their own material, they can. If they want to look at specific things, we can dive into it and explain it and all that kind of stuff. So that'll just be a very free form final session where we're going to really just do full out tech. Also make sure that you go and look at our associate Deb Bryant's keynote this year, Open Source and Telecom, What a Difference a Decade Makes. She's presenting on Thursday morning. You go ahead.
All right. Yeah, thank you guys for coming. My name's Doug Smith. Life and I work together on the same team called NFV Partner Engineering in Red Hat's Office of the CTO. Both of us have been Asterisk guys for a long time. I mean, Life has been an Asterisk guy for an even longer time. You probably know his name. He's decap number 4, we figured out last night. So he's seen a lot. At any rate, NFV is Network Function Virtualization. If you'd come to our talk last year, we kind of dove into what that means. And last year was a lot of theory. This year is going to be more about the practice of how we kind of implemented the stuff that we went over last year.
Yep. Leif Madsen, DevOps team lead on the NFV PE team, worked with Doug, and he basically said everything else that needs to be said.
So containers. Everything that we're doing here is with containers. So as you might be familiar with Docker as a technology, and that's one approach to containers, and it's one that we use. We also use other container runtimes. Just a show of hands, who here has used Docker or containers otherwise for any purpose? All right, yeah, all right, a good amount of people. I won't hang out here long. You can go to the next slide.
All right, cool.
So in Kubernetes, which is a way of orchestrating containers, we have the idea of a pod. And I'm kind of just bringing this up because this is probably things we're going to say over and over again is containers, pods, Kubernetes. So a pod is basically a logically grouped set of containers, and they share a container, which is really a namespace in Linux. And you would put like containers together, or otherwise you have kind of
single. You might have just a single container in a pod. It doesn't always have to be multiple.
Right, and it would just have it connected to that infra container, the kind of shared container stuff like your network interfaces, your storage, yada yada. You can go on from there. So we're talking a lot about Kubernetes, and we use it here extensively and exclusively in this particular case. And in short, Kube is at its very core is a scheduler. What it does is it takes your workloads and it assigns them to machines in order to run them. And it follows your instructions on how many of that workload that you want. So you say, I want Asterisk, I want 5 instances of it, and it will make sure that there are 5 instances of it up for you.
Yeah, it orchestrates across multiple machines too, so if a machine goes away, it can reschedule them and move them somewhere else. It can monitor for oversubscription of the node and actually move workloads around or make better decisions as to where those workloads get scheduled. So you just say, I want a thing. I want box ABC to be instantiated, and it comes up, and the whole point of Kubernetes is that it's able to understand what's going on at the infrastructure level and schedule things in a smart manner. Also, we'll probably interchange OpenShift with Kubernetes. You can assume they're effectively the same thing. OpenShift is the Red Hat distribution, which is further along, actually. So anyways, I just want to make sure if I start saying OpenShift, then we're good.
So Kubernetes, it's part of a foundation called Cloud Native Computing Foundation. So you've got Linux, and you've got the Linux Foundation, right? So that's kind of a like open governance model to make sure that, say, one evil mega corporation doesn't run away with it and take that away from the community. So in the Kubernetes world, similar thing, CNCF, Cloud Native Computing Foundation, and that's actually part of the Linux Foundation. And we kind of wanted to define what cloud native is. So we said, whose better definition to take than that of the Cloud Native Computing Foundation itself? And really, there's kind of 3 components to this, which is one, you take your applications and you package them in containers. So sort of 2 parts to that. You have an image, which is sort of the disk that defines what's inside that container, and then the container itself, which is really an instance of that image running a process. And secondarily, you will have those containers be dynamically managed. So when we say dynamically managed, generally we mean with some type of orchestration system. And in this particular case, what you'll see is with Kubernetes. So we've said, Kubernetes, we're going to express our intent on how to run these containers, and it's going to try to fulfill those requirements for us. So this is kind of a concept that we use is we want an intent-based sort of system. So that we say, here's what we want to do, and then Kubernetes goes and does it exactly. So instead of, say, having a set of 3 or 4 boxes, and you go and SSH into all of them, and you put your workloads exactly where you want, instead you say, Kubernetes, I have this cluster of 4 machines, and I want to run 4 Asterisk instances. And it says, OK, given the compute resources that are available, I'll schedule 2 on this machine and 1 on each of the other machines. And then lastly, we want these to be microservices oriented. And really by that, we mean that these are lightweight processes that you can spin up and have die at any time. Now granted, we live in a different world than those who live in the world of just simple HTTP REST applications. In the networking world, we have a lot of considerations that are stateful. And these aren't always considered by those that live in the web scale world. So I think you should strive for a microservice oriented, but I think the reality means that we're going to have some processes that kind of
they're long-lived.
They're long-lived, and they have other considerations. So I think this is something you should strive for, but reality is a beast that we have to handle. And
the big one is breaking the components down into individual pieces that have their specific reasoning for existing, so that you don't have these big monolithic applications where you build all of the components into one kind of giant blob. The idea is to break them all apart, let them lifecycle manage themselves independently of each other. And that's really what you're striving towards for a microservices system. Cool, so kind of talked about this a little bit last year, but we'll reiterate upstream and downstream, so projects versus products, and how open source is productized. So this is Red Hat's model. This is how we approach all of our products. So we have an upstream or an open source component, which is the source and foundation of where all of the source code goes. So all of the work happens in the open source first. So basically what happens is there's a bug filed by someone, or there's a new feature created, or something happens and some source code is done. that gets put into what we call upstream, which is the open source version. And then what happens is periodically Red Hat will effectively take a snapshot of that. So in the case of, say, OpenStack or Kubernetes, there's a new major release. That's kind of the point of saying, okay, we need a new snapshot. There's a new major version that's just been released from the upstream community, and we are now going to stabilize and productize that. And so what we do is take a snapshot of that, we downstream that, and so now we have a controlled set of code that we're able to deliver to customers, and they're able to obtain subscriptions for those applications. So what we end up doing is when we're doing the stabilization process, all changes that would go into the downstream always go into the upstream first. They always go into the open source version, get signed off from the open source community, and then we effectively take that and put it back into the downstream. So there's no black magic, there's no forking, there's no specialization in the downstream product. It's always all upstream first, and all we're doing is stabilizing it and pulling down specific bug fixes and making sure that we understand exactly what code is being shipped. So that's, when we say upstream and downstream, that's what we're talking about. So one of the examples of a downstream product is OpenShift, which is the Red Hat distribution of Kubernetes. So all of the work that's done into Kubernetes, there's effectively a snapshot done at each major Kubernetes release, and so we work on stabilizing it and packaging it, and providing some other tooling and validating and testing that it interacts with other applications that we expect all our people to be using and stuff like that. And when we find a bug, that goes into the Kubernetes upstream, and then that makes its way through its life cycle into getting merged, and then it comes back downstream. So when we're talking about OpenShift today, and which is what I'll be showing on the demo, that's the Red Hat distribution of Kubernetes. It's still, there's free versions of that, just like CentOS is effectively the free version of RHEL. OpenShift has its own open source component, and then of course there's a subscription model if so be it. Also going to be talking about Ansible. Ansible is an agentless configuration management tool. It uses SSH connections and Python to do automation. So we use things called playbooks, which are defined using YAML, which is fairly easy to read, and has great documentation on the modules that you use. Every time I'm writing Ansible, I pretty much, first thing I do is load up the modules list and make sure I have all the correct syntax and all that stuff. And so we're going to be doing automation and leveraging Ansible kind of throughout the day. Also going to be talking about the automation broker. So the idea behind the automation broker is within Kubernetes and OpenShift, there is a service catalog, and so the automation broker leverages that so that you can provide a nice, easy way of installing applications. And so the automation broker, in our case, is going to be using APBs, and APBs are Ansible Playbook Bundles. So Ansible doing automation to spin up our Asterisk application on top of Kubernetes.
We're also going to have a session this afternoon that's specifically about operators. And this is just a super heavily overloaded term, and I'd say doubly so in our particular space, because I always think of like a press 0 for the operator, or a switchboard operator, which maybe is a bit obsolete, but So the idea behind an operator is that it's a Kubernetes application that manages other Kubernetes applications. And it's called an operator because you program your operational knowledge into this application. So basically, it's going to give you a way to lifecycle manage your applications, but with intelligence that's specific to your particular deployment. So if you have special things that you're doing every time that you bring up an application, for example, instead you're going to program that logic into this application. So at scale, this is a big deal. And especially if you're already otherwise integrating with Kubernetes, this is a big deal because it gives you a way to manage the stuff that's specific to your deployment or specific to your business requirements. So at a small scale, maybe you don't want to spend the time to make custom logic for that. But if you're going to scale up and go bigger, there's a good chance that you can really have a big payback here in like your operational overhead by putting this kind of logic in there. So later today, what we're going to do is show a demonstration of using operators with Asterisk. And basically what we're going to have is we're going to bring up a cluster of Asterisk boxes, and we're going to have them service discover one another and create trunks to all those Asterisk boxes, and then we'll make some calls. So instead of, say, taking all the time that you may take to set up a bunch of SIP trunks, and you go through the future of telephony and use the Tokyo to New York example, which I've done like a million times, we can just like make a couple dozen SIP trunks just with the application. Now granted, it's a lab environment, so it's really known what's on each end, and I know sometimes the reality is, you connect to an ITSP, and it's a big deal to like take a bunch of PCAPs and go through all that stuff. But in this particular case, we're gonna know what's on each end, and we're gonna be able to make these SIP trunks automatically, and we can just make a little cluster that knows how to service discover itself.
Before we move on, I think we've said lifecycle management a few times, and maybe it's good to define what that just kind of means. All we mean is the lifecycle, or the once you instantiate an application, there's a version of it, and there's that instance of it, and you need to be able to move to another version, or I've made a change to the source code, and I need to be able to redeploy that and move that on. So what we're talking about when we talk about lifecycle management is taking from one version and being able to move to the next version. So you might spin up a pod that's running a version of an application, and you might spin up another pod that has like the next version, and then like moving your traffic over to that. Well, there's a lot of things that can be involved in that. So maybe there's a schema change that needs to happen in addition to the code changes and all the things that happen. So when we're talking about lifecycle management, what we're talking about is the ability to move from version to version in a sane way.
And that's the big picture for sure, is like, your application is going to have a life longer than a single instance of it, and your versions are going to change. But when we say lifecycle, we even mean it at the smaller level as well, which is when we have an instance comes up, it lives, and eventually it dies. Yeah. So it's from everything from the birth of that application to the death of it, to its upgrades, to changes in its family when the schema changes in
its
a database.
Configuration.
So there's a lot of that there to that picture. So what we've built this year is kind of an extension to what we presented on last year, which is VNF Asterisk. So as I mentioned earlier, we are part of a team that's called NFV Partner Engineering. That's Network Function Virtualization. And the shortest story for explaining that is, in the telecom world, people want to move away from a model where you have a really long life cycle for your functionality that you have in your network, and that functionality may exist in like a application-specific integrated circuit. It's silicon that you have punched, is that the right word? Whatever, you put it in a bath and you get all your circuits out of it. And that's like a super long lifetime, that's like a 10-year plus.
Yeah, for your ROI,
right?
Your return on investment, because it takes a lot of money to build that stuff.
So what they want to do is they want to virtualize those network functions. So instead of having an ASIC, the application-specific silicon, they want to go and run virtual machines that can do these functions. So those functions we call VNFs, virtual network functions. Part of the gist of our talk last year was that if you're somebody that uses Asterisk today, you're actually way ahead of the big telecom companies. And I know it can be frustrating in the telephony world to feel like some of this stuff does move slowly, and with my ITSPs and all of this, and you see that kind of telecom culture that things move slowly. We have a strong reliance on reliability, et cetera. But if you're an Asterisk user today, you're years ahead of where these telcos are, in my opinion. So that was kind of a big message of last year, and I just kind of wanted to reiterate that. So VNF Asterisk, you can hang on this for a sec.
Yeah, sure.
Is basically we needed in our own lab environments a way to say, hey, here's a VNF that we know and love, and we can dissect it easily. And we thought the Asterisk would be great for that. So basically what we did is we kind of packaged it up and made it in a particular way that made it really flexible. I think we can go to the next slide now. So basically what we tried to do is we said, all right, I want to spin up an Asterisk, but I kind of want it to be a clean slate. So what we did is we spun up an Asterisk, and then we had a controller. And the idea of this controller is to express our intent, as I mentioned before, for what each of these Asterisk instances should do. So that's part of, like we mentioned before in the kind of definition of cloud native, is dynamically managed. So
we're doing push configuration into these. When the Asterisk comes up, it has just enough configuration to be on the network and be alive. Other than that, it's dumb. It doesn't actually know what it's supposed to do at that point.
Yeah, so we would push almost everything to it. We'd have like some like skeletal etc asterisk star.conf files to say like, oh yeah, well we want CDRs and we want to load these particular modules, but we'd have no dial plan. So, and we'd have no SIP endpoints. And we'd have that controller go and push those configs with ARI push config and using sorcery to put that there. And then additionally, we would have the Asterisk pods. And in this case, they did have multiple containers in each pod. We'd have like a Homer capped agent. You probably can use hep.conf, but in our case, we use the capped agent to send that stuff to Homer so that we could see exactly what's happening. And this was definitely another theme of last year, is the more dynamic your configuration is for Asterisk, the more that you need to double down on how you monitor it and how you centralize your logging. Because when this stuff is more fluid, it's not that you can't just have your sysadmin necessarily just go SSH into this box and know that the workload is there and it's running. More or less, you want to be able to say, let's look at this platform as a platform. So let's have monitoring that's centralized. Let's be able to look at it all in one place. Let's have our logging all in one place. So that stuff becomes, more and more.
Because you got to remember, these instances are now fluid. Every time you up a version, you're not upgrading it necessarily. You're actually throwing away the Asterisk instance and bringing up a new one. So everything just kind of changes the way that you approach the problem.
Your post-mortem is going to be different. You can go for the next one. So this is even some more detail of that last diagram. And this is kind of how our pods were organized. So generally, what we've got here is we've got Homer. It's got a number of components to it. So it's got a database, it's got a UI, and it's got, at the time, it had a Comma-Ilio server to pick up all the HEP packets, which contain the monitoring. I'm pretty sure Homer does not need the Comma-Ilio to do this anymore since this happened. So that's getting better all the time. But in each of the Asterisk instances, we had Asterisk, and then we had the capped agent. So those were kind of, it was a good example of multiple things in a pod, multiple containers in a pod. And something that I guess is also just worth bringing up real quick is in a container, you have one process that's in the foreground. You can run more than one process in your container, but generally you want to have one process per container, and in this case, we needed to have two. But the important one is Asterisk, and we run that in the foreground for a very important reason, which is your scheduler, whether that just be Docker run, name of the container, or Kubernetes, it doesn't know if that pod or container is alive unless it knows that that foreground process is running. So we said, yes, Asterisk, you run first, you run in the foreground. If it dies, scheduler knows, and it can create a new one for you. And I think that concludes what we've got for our technology overview. So, bunch of technologies, a lot of stuff. Matt, go for it.
Sorry. Can you go back one slide? How come you decided to use the Homer capture agent as opposed to the built-in Asterisk module for Homer? Was there a problem with the built-in one?
No, I don't. Honestly, I think
Experience.
And you know what I think I had capped agent images hanging around, and when I was drawing out the diagrams, I thought that it looked good to have those two together.
Yeah, it was. It looked better. It's pretty.
I later realized
we could have just used the built-in.
Yeah, I could have just set hep.conf and.
Well, one of the problems with the built-in, and I don't know if Homer capture agent gets you around this, is that Asterisk would need to know the address of the Homer server in order to direct traffic there. Which, if you're trying to be super scalable here, then you got to punch environment variables in.
Well, you push it in from the controller. The controller would tell the Asterisk where to point to, because in theory, you could have multiple. If you had a tenant kind of set up where you're going to have like a bunch of blue asterisks all together, and it's going to have its own Homer, then you might have to redirect them to different places, right? So you dynamically push the configuration for where to talk to.
And certainly something that will come up in some of the demos this afternoon and what we had last year is this idea of service discovery. And so that was definitely part of this, is that Homer would have to say, hello, I'm Homer, I'm alive, and I live at this particular IP address, which we don't know in advance because it's dynamically managed. So it would say, hi, I'm Homer, I live at 192.168.1.100 or whatever. And then we would have to spin it up with the capped agent and say, capped agent, hey, you got to talk to Homer's here. But there's no reason that we couldn't have done that with the hep.conf, because we can template that configuration when the pod starts up.
So that raises a bunch of interesting questions, right? So let's say I've got a Homer that spins up, and so typically I would want my Asterisk configuration files to be part of the container so that my configuration is immutable and all the nice things that come along with that. Generally, we've in the past used environment variables in the container when we start up the container to inject like IP addresses and other things that depend upon the environment into the container when we start it. But if I've got a Homer server that spins up, I don't want to have to restart or redo all my Asterisk containers in order to get the new address in there. So how do you guys manage
So the way that I would recommend it in a production system is, if you're using Kubernetes, I would say to use the concept of services, which is basically a way to say, amongst other things, this particular DNS name has an affinity to this particular service that's running. So I would say, all right, spin up, let's just say it's, for the sake of simplicity, Homer UI. And I don't want somebody to have to memorize that or somehow discover that it lives at this IP address. With the service, I can say, okay, hey, we have homer-ui.mycompany.org. And you would go there, and then Kubernetes knows how to redirect that to
within its own internal network.
To the Homer UI. And you can use that for other services as well.
Yeah, so that way you can point a route at it, for example, which is like a DNS address for that service. And then if you change the Homer version and you have to like throw that pod away and spin up a new one, the service continues to live there and points at it. So there's nothing changes from the front end.
Yeah, so I think in some cases, in our particular example, we wanted to try to make things as dynamic as possible, but Kubernetes actually has plenty of tools that are sometimes more real-world useful than our particular example. So like services would be one of those examples that we probably could have leveraged better or might fit a real-world scenario a little bit better.
Yeah. So, all right, so we're starting on the next section in supposedly 1 minute. So how about we take a 2-minute